So in this lesson, we'll see how datasets and data loaders can be used to load and iterate over Fashion MNIST dataset. Now, if you haven't heard about MNIST, allow me to do a quick Google search and show you. This is the famous MNIST dataset, MNIST. Why is it called MNIST? Well, it's because it's short for Modified National Institute of Standards and Technology Database. This is the sort of the original version of MNIST. This is how it came about, the origin of that. It's a large database of handwritten digits that is commonly used for digit recognition tasks. And this has been around for quite a while, actually. It's been around since 1998. And if you look at a quick summary of that, it's a large database of handwritten digits that is commonly used for training various image processing systems. So earlier days, when you try to do some sort of digit recognition, whether you're using a neural network or not, this is kind of the sort of the benchmark at the time. The black and white images from NIST were normalized to fit into 28 times 28 pixel bounding box. And this is quite important because you see later in the code, you see we do some sort of dimensions, reshaping the data. You need to know kind of just how many pixels times how many pixels, because that's going to affect your dimensions in your tensors, right? It initially contains 60,000 training images and 10,000 testing images, and this is useful information, I guess, because later on we also have the Fashion MNIST. What we're gonna be using is Fashion MNIST. So Fashion MNIST looks like that. Take a look at. Let me show you an example of it. So Fashion MNIST is a data set of Zalando's article images consisting of a training set of 60,000 examples and a test of 10,000. So same thing here. They also give you 60,000 examples, give you 10,000 test examples. Each example is also a 28 times 28 grayscale images associated with label from 0 to 9, so 10 classes. All right. So if you take a look at Fashion MNIST, let me just go into the images so you can take a quick look at it. We're gonna run that anyway. So you have all of these images and you're trying to classify them, whether this is a shorts or a skirt or dress or blouse, sneakers, shoes. So you're trying to classify them, all right? So Fashion MNIST dataset is a large, freely available database of fashion images that is commonly used for training and testing various machine learning systems. It was intended to serve as a replacement for the original MNIST database for benchmarking machine learning algorithms. It shares the same image size, data format, also has 60,000 and 10,000. So 60,000 for the training, 10,000 for the test, right? And the set of images in the Fashion MNIST database was created in 2017 to pose a more challenging classification task than a simple MNIST digits data. So people were looking at the MNIST digits data, and they were quite consistently arriving at accuracy of 95%. So sometimes even up to 99.7%. So it becomes too trivial to some of the more state-of-the-art neural networks. The researchers decided that, okay, well, maybe it's time to come up with a more complex data set, and so the Fashion MNIST was created for that purpose. And you can maybe read more about that if you want to, but this is enough information, so let's close it out. So we'll see how datasets and data loader, so the datasets data loader, how can we use that to iterate over Fashion MNIST dataset, and then we'll talk a little bit about how if you have a CUDA compatible GPU, you can modify some of this to make it work by moving your training and test data onto the GPU for faster training. So I'll also talk about that, because this sales series, I just want to assume that if you have a GPU, I want to teach you how to take advantage of that. And I'll also show you how to use Lambda functions, transforms, to there's this thing called a transform and also a target transform, and you can use them combining with your Lambda transforms to apply some sort of arbitrary functions to your data, which could be helpful in pre-processing your data before you start constructing your neural network and feeding it data. I'm going to save you some time. I don't want to type it all out one by one, so I pre-written all of the code, and I just want to maybe run through it and then maybe explain how to work with data sets in PyTorch. So first thing is, where do you get Fashion MNIST from? Now, if you don't have them, you can actually just install them. You can just download them directly from the code here. So what you do is you import torchvision.datasets. So very interestingly, when you first install PyTorch, you have Torch Audio, Torch Vision, and all of these different sort of like sub-modules that are more specialized for different tasks, right? And torchvision.datasets, they include a couple of datasets that you can use, that you can bring in. And so one of it being Fashion MNIST. So all you need to do is really just say from torchvision.datasets, import Fashion MNIST. But this is a PIL image format. So PIL stands for I believe Python imaging library. And so what we want to do is we want to convert this from a PIL format to a tensor format, right? So the way we do that, we use toTensor, which is also pre-written for us. We just have to bring in from the transform. So very convenient. A lot of the code that you expect to write, you could actually just import them, and you didn't even have to write your own. So you bring in transform so that you can convert this from a Python image library format, PIL format, and convert that to a tensor format, which is kind of what you need. And this is not really needed, but I just wanted to bring that in so I could also show you and visualize that for you, right? So let's take a look at code from top to bottom. So training data and test data. So training data and test data, the only real big difference is if you set train equals to true, it's gonna just download the training data set. So that's the 60,000 data, right? Train equals to false is gonna download the 10,000 test data set. And then once you have the two of them, you can also specify a root. Now root is the path where the train and test data is stored. So in here, I'm gonna say create a folder, the directory is called data. And when you set download equals to true, it's gonna download the data from the internet if it's not available in this folder. So it's gonna look in data and say, hey, do I have that data? Well, if I don't have the data, I'm gonna just go ahead and download that. And then they're gonna be put into the data set in here, all right? So this is also doing the same thing. So basically saying that if they don't exist in this directory, and it says, well, do I have them? If I don't have them, download, all right? And then do tensor converts a PLI image on NumPy and the array to a float tensor. You could also write that on your own. You don't actually have to bring it in, but since it provides you a clean, nice utility function, you might as well just make use of that. So here we're saying that once you bring that in, don't use the PL image, but rather transform them into tensor. And you do that for test and train. So this is what line 14 to line 29 is doing. For the labels itself, I told you that you're gonna have a it's a 10 class classification, right? So basically there's 10 classes, but they're all in different 10 classes of fashion items, and they're all coded into like 0 and 1 and 2 and 3 and 4. That's not very intuitive, because if we see an image and we say this is a class of tree, we would rather see that there's an image and it's a class of grass, right? Or if you see something like, okay, here's an image and this is a class of 6, it's not very intuitive. What we would rather see is we see an image and we said, well, that is predicted to be the class of shirt, for example. So what we do is we create a simple dictionary. We said labels map equals to put the dictionary in there, so we could just map it in here. And we look at each of the images in the training data, and then instead of actually having the labels map as the title, instead of having the class index like 6 or like 3 or like 9, instead of having that, we're gonna have the labels map instead. So what we do is a very simple for loop. And what is this for loop actually doing? We're saying that how many rows, how many columns. This basic, all of these are basic matplotlib stuff. If you know anything about matplotlib, this should be quite intuitive, right? So we set up 4 rows, 4 columns. So 4 times 4, that's 16. So what this would do is 4 times 4, 16 plus 1, that would be 17. So it is going to run, this loop is going to run 17 minus 1, because that's where you're starting. This is where you're ending. So it's going to run 16 times. It's going to populate that subplot for you. And each one of them, what you're going to do is you're going to take the training data, and you're going to just take so training data start from number 1, training data start from number 2, all the way up to 17, right? And then once you're done with that, put a plot title on each one of them, and then turn off the axis, and then finally show them in gray, because we know this is our grayscale. And the rest is not really important. You could comment them out if you want, just remove them. And let me just run all of this first and explain that. Okay, so I'm going to run python datasets.0.py, and what do we have? We have a nice matplotlib. And so this is image number 1. That's a code. It predicted as a code. No, it's not predicted, but there is no prediction here yet. It's just basically plotting out the label which you downloaded, right? So code, angle boot, sneaker, trouser, shirt, sneaker, dress, coat, pullover, shirt, shirt, coat, bag, coat, t-shirt, dress. All right. So if you want to change so for example, if I change this to, instead of 4, 4, if I say 3, 3, then this would be 3 times 3 equals 9, plus 1 would be 10, so 1 to 10. So there'll be 9 images in total. So if you run that again, so now you see that this is a 3 times 3, right? So that's really what it is. Nothing fancy in here. And so what we did from top to bottom is to just download that. And if you first run this and you don't actually have a data folder, or you don't have the images in the data folder, it would go ahead and just download that for you. But if you have it, it's not going to do anything. It's just going to use the one that you already downloaded. All right. This is cool, but let's uncomment this and let's talk about data loader. Why do you need to care about data loader, right? So you have the data set. Now data set, retrieve your data set features and labels one sample at a time. When you're training a model though, in real life, when you're training a model, you typically want to pass samples in mini batches. So you actually want to pass your samples in mini batches, right? So you put them in mini batches because you will train them using this method called either sometimes you hear the mini batch gradient descent method, sometimes you hear the batch gradient descent, or you hear the stochastic gradient descent. We'll talk about all of that later. but you put them in mini batches. You will reshuffle the data at every epoch. So every epoch, meaning every one cycle, sort of. You would do that. You will reshuffle the data to reduce model overfitting. And then you would also try to write some code. If you're trying to write all of this on your own, you would also use Python's multiprocessing. So you use Python multiprocessing module to sort of speed up this data retrieval process, right? Now, if you want to write your own code, you can. You just have to bring in all these different ideas, and you can say, well, shuffle them, and then use multiprocessing, sort of put them into different batches and stuff. But what you can do as well is you could just bring in data loader, because it does all of that for you, right? So data loader does all of that for you. It supports both map style and iterable single multiprocess loading, customizing loading order, and there's a lot of other things that it does for you, including shuffle, including sampler, if you want to include that. Instead of writing the code to do all of this manually, you could have just said data loader, and you pass in your data. So training data is what you have here. This is what you name it, test data. You want to pass them in. Then you specify your batch size, and you specify whether you want it to shuffle or not. So if you want it to actually shuffle the data, reshuffle the data at every epoch, then you could just say shuffle equals to true. And because this is a sort of a hyperparameter, we could maybe put it all the way up there and make it a bit cleaner. And let's actually, just to make sure that we understand all of this, let's go and run this in iterative mode. So I'm going to say -i, and I'm going to say dataset0.py. I'm going to close out that one. What you're doing when you say -i is that you're running this in interactive mode, and you're actually going to, it's going to stop at the plot.show, so you need to exit that for it to continue running, and then return the terminal back to you. If I show you what we did with the training data, I'm going to zoom in a bit so you can see better. So to take a look at what is the size of this training data, you could just use Python length training data, and you see there's 60,000. I'm sure you can do the same thing for test data. So let's see, test data, it's called, so it's spelled that correctly, 10,000. And if you want to take a look at, let's say, only the first example, you could just go ahead and say training data and just index it like that, just 0. That's indexing the first training sample. So run that. Now you see all of this is kind of what gives the first image. The first image, right? It's basically just using a matplotlib to sort of plot out this one. And because it's grayscale, you don't have 3 dimensions, don't have 3 channels, you only have 1. So this is a value 0 being all black, and then a value of like something like 1, because it's normalized, would be all white. And most of the values will fall between 0 and 1, and you see that some of them are very close to black, some of them are very close to white. If you were to visualize this sort of matrix, if you want to think of it like matrix, if you want to visualize this ND array, then you would see the image of a blouse or a bag or a shirt, right? If you take a look at this output, right, this is kind of a tensor of a shape of 2, right? So you have this is the first element up to this point, that this is the second element. So how do I get the second element? I just have to say 1, which is the second element, because 0 indexing. So this would be the first element, second element. So let me run 1, and it will tell you 9. So what is 9 again? Let's go and take a look. So the first one will be ankle boot. Okay, the first image in the dataset would just be a ankle boot. What about the second image? That would just be what? That would just be a t-shirt. Okay, and remember how I said about the this data loader would just put them into mini batch, and then in this iterable, you can iterate over that, and you can, and when I say you can iterate over that, what I mean is you can actually go ahead and say something like, to create an iterable. Let's actually do the training data. So the training data is passed into a data loader function, and it outputs train underscore data loader. So let's do train data loader, and this will create an iterable. So if you know anything about Python's iterable, you know that you could use next and call on it. So I could say something like next, like this. And because it returns 2 values, the first one is the training. These are all the features. This is the actual target, or the label, right? This is the features, this is the label. So what we could do is to basically do an unpacking there and say train features, train labels, and we just unpack that by doing next, right? And if we were to do that, if we say train features, let's call the size and see if things are still correct. So you see that there is the 64. Where did 64 come from? Now 64 come from the batch size. So it's saying that, well, there is a, if you want to think of it like an ND array, right? The outer dimension would be 64. There are 64 because one batch will contain 64 different images. So 64 images. Now each image, that's one, will contain 28 times 28 rows of pixels, 28 columns of pixels. That's because the image is a 28 times 28. We learned about that earlier at the beginning of this lesson. All right, so we have 64. That's in your batch size, 1 times 28, 28. That's all correct. We verify that quickly. What about train labels. That's 64. That's also no surprise because each image they will have one label telling you that, okay, this image corresponds to a ankle boot, a coat, a sandal, a shirt, a sneaker. And what's useful is you could do something like take the image and say take the first. So I have 64 different images. I want to take the first image, for example, right? I want to take the first image. So I could actually do another indexing and I can say just take the first one. In fact, what you could do is you could just shake off the dimension of size 1. So this is the dimension of size 1. You could just remove that by doing squeeze, and that will just drop the dimension with a size 1. So let's just run that, and if you print img.shake now, you see 2828. Okay, that's cool because we're taking the first image, so that drops that off, and then we also squeeze away the 1, so now we have 2828. And now you could go ahead and just do a plot.imshow, and because we name it img, I'm going to call it img, and we gonna give it a color map because this is a grayscale. We want to just say gray, otherwise it's going to use the default, which is not grayscale. All right, so let's run that. Okay, you created a plot. Let's show the plot. So plot.show, and then we have the first one. So this is quite clearly a sneaker, so we expect to see 7. All right, that's a sneaker, and let's close it out. Now you could also go ahead and verify that the first label is in fact a sneaker. So let's go ahead and say print train labels. Did we name it labels? Yes, we did. We named it train labels. This is a tensor of size 64. That's the dimension. So we want to take the first value. So let's just say take the first one. And in fact, we actually see 7. So that's correct because it is a sneaker, right? We verify that. Now I say that what if you have GPU? What if you want to move these tensors onto your GPU, onto your CUDA, if you have a CUDA compatible GPU, right? Now in the earlier video in this series, you see that I use a technique like device equals to CUDA. That's actually quite common. You can say device equals CUDA if torch.CUDA.is available. So that's how you know you have a CUDA compatible GPU. Else, just continue to run it on CPU. So you can do something like this. So this will assign one of these value, either CUDA or CPU, onto a variable called device. Okay, so let's run that. Let's take a look at my device. It's actually CUDA because I do have CUDA set up on my computer because this is kind of the whole series. I want to just focus on GPU and CUDA later on. So if you have a CUDA enabled device and you want to move, for example, you want to move these train features. Where's the train features here? If you want to move the first batch, so the first batch is has 64 images, correct? This is train features. You could go ahead and say something like train, name it train features. We name it train features, and we can just say 2, and we can either just put CUDA in here, or in our case we just have to say device, because it's going to be CUDA if torch.CUDA is available, else it will be CPU. Okay, so that's one way to just move everything to CUDA. If we run that, now it's going to move everything to GPU, and now it verifies that all of that, the 64 images, all of this, the tensors are all now moved to your CUDA device. Okay, that's one way to do it. Another way, if you don't want to move all of that, for some reason you don't want to move all of the whole batch, you only want to move specific examples, you could use something like a for loop. You can say for, let's say 4 inputs and 4 labels. And because we've done that on train data already, let's try the test data. So we can say test data loader. If for some reason you want to do it in a for loop and not move the whole thing, you could say something like input and do the same thing here, move to device. And device would just refer to CUDA in your example, and you can do the same thing for labels. And that will also move everything to CUDA. So that's the second way to do it. The third way to do it is if you look all the way up here, there's the training data. You could move all your train data, move them all onto CUDA far in advance. You can move them all in advance. So you could actually have the train data and test data all moved to CUDA from the get-go, from even before you start to construct your neural networks. All right, we load in training data and test data. So what we do here is we say something like training data, and we say data.to device. We don't have device yet, so we say device equals to CUDA if torch.CUDA is available. And that will move the data side of the data, meaning all of this, the images, right? These are the inputs. You'll move that to GPU. But you also want to do that for your labels. So you want to set labels and also move that to device. So these are 3 different ways you could move your training data, your test data, move your tensors onto your GPU, and then use GPU for training. Now I do want to make a note here that Data doesn't always come in its final form, final process form that is required for training machine learning algorithms. So when you see a transform here, this allows you to actually insert your own code here to perform some sort of manipulation. Now, in terms of transform, there is two kinds of transform. One is transform, another one is called target transform. So what is the difference between transform and target transform? Let's put a quotation so it doesn't complain about that. Let's talk about the difference between the two of them, right? Transform and target transform both perform some sort of transformation function onto your tensor. But the difference is target transform perform this transformation onto your target, which is basically your labels, and then your transform perform it on your inputs. So earlier you see this is the inputs, this is the output. So this is the target, we call it the target, right? So these are the input. This is what you want to pass, this is what you want to feed into a neural network. This is what you ideally want it to predict, and say, okay, this is a class of 9. So that's your target. So when you put something into transform, it's going to transform only the input, not going to touch the labels. But when you do target transform, it's going to transform this value. So in summary, transform, you use transform to modify the features meaning this one, the input, and the target transform, you use that to modify the labels, the target, all right? This accept any kind of callables, including your transformation logic. In transform, because the fashion MNIST, we talk about that, it comes in the pure image format, the Python imaging library format, and the labels are all integers. We need to just put them into call2 tensor and to just transform them into tensors, because you want to have all of these in tensors. And then target transform, what do we need here? Very commonly, we need the features, right? Let's put a comment here. We need the labels as one hot encoded tensors, right? So very commonly for training a neural network, we need the input, we need all these features as normalized tensors. We normalize them into a scale of 0 to 1. And then for the labels itself, we want them to be one hot encoded tensors. So what does one hot encoding means? So open up the browser again. So this is one hot encoding. So it basically says that if I have a class of like 1, 2, 3, 4, what I want to do is I want to transform this into this shape of take rate and put them in its own column and say, okay, for ID number 1, for student number 1, well, is it a red color? Yes. So red will be a 1, and blue and green will be a 0, 0. And student number 2, it's a blue. So what's going to happen is the red will be 0, green will be 0, and then blue, for student ID number 2, it's going to get a 1 in the blue. And student ID number 3, it's let's say green hair. So it has 0 for red hair, 0 for blue hair, and 1 for green hair. And blue again, so blue is going to be 1, right? That's one example. Let's see if there is another example. And you can see a lot of the times when you train a neural network, you don't actually want this to be stored as categorical. So in this case here, right, same thing here. So the point is 25, you carry that over, but team is A, so you have, because they're all together 3 different classes, you have 3 different extra column, team A, team B, team C, and this is A, so it would have 1 in A, but 0 for each one of them. So this is kind of the main idea behind one hot encoding. And this is really useful when you try and train a neural network. You need to basically take your class label and you want to put them into one hot encoding. So how would you do that? So let's create some fake data to work with, and then we could see how to do a one hot encoding, right? So let's clear the screen out. Let me just create a script, maybe use least comprehension for that. I'm going to say least comprehension. I want to say lambda, and then I want to say take each of the unit in here and square them. Okay, so square them on x for x in a range of 4. So that would be 0, 1, 2, 3. So if I run that, so 0 would be squared would be 0, 1 squared would be 1, and 2 squared would be 4, 3 squared would be 9. All right, so very simple least comprehension there, nothing fancy. And what I can do, because I have torch imported in there already, so I could actually go ahead and say something like, I don't actually want a square. I want to first create a zeros matrix. So I want to just say something like, take this, say torch.zeros, put 10 in there because I expect to have value 0 to 9, right? Because this, in my actual code itself, in the actual data set, in the training and test data set, I actually have the labels and they take a class between 0 and 9. So I actually want to have a 10 times 10 zero matrix. So I'm going to say this. This is a one-dimensional, so you don't have a 10 times 10, you just have 10 different zeros, right? So I don't have, if I put 10 comma 10, then it will be 10 times 10, but here I'm just saying a one-dimensional, so I have 0, 0, 0 all the way 10 times, and I have that for altogether 4 times because it starts from 0 all the way to 3, so 0, 1 to 3, all right? So in a way, this is actually already creating a canvas, and all you need to do is to fill that value in. So You fill the value in by using scatter. That's one way to do it. So you could pass in the scatter, and you want to apply that in place. So underscore, this is something we spoke about in the earlier lesson. If you are unsure about any of this, what is in place, look at the earlier video, right? So I want to implement, and I want to say apply that on the dimension 0. So I'm going to say dimension 0. Apply a value on what index, on which index. I want to say take the index and look at this value itself. So I want to say index equals to torch.tensor x. The first one will be 0 rather. So it would just apply that on the index 0. And then the second one will be 1. So it will apply the 1, and then 2, and then 3. Okay? But you haven't said what value you want to apply. You only say that, okay, I want to apply a scatter. I want to modify the value in this location, but what do I want to apply there? I haven't actually mentioned about that. So I also want to have value equals to 1, because that's what a one-hot encoding is, right? 1 or 0, 1 or not. Okay? So let me run off that. In the first element in this tensor, you will see that the index 0 has been modified with a value of 1. That's what you did here, right? That's the index. Then the second one, you modify it at the index of 1, and then you modify it at the index of 2, and you modify it at the index of 3, each time replacing the value with 1. If you want to, you could say value equals to, and then x to the power of 2, or x squared, or x to the power of 3, you can do that, and it would just replace that. But that wouldn't be one-hot encoding, would it? So we wouldn't want to do that now, but this is kind of correct. And now you could remove that, and you can pass in this lambda function. And the way you do that, you will need to bring it in from a lambda. So this is the 2 tensor. I want to put a comma, bring in lambda. So it's really convenient like that. It gives you a lot of this utility. So I could say lambda, and then I'll pass in my lambda function. Now I don't need to create the fake 0 to 4 data anymore. So I'm gonna have to refactor it a bit. For example, I don't need this. If I want to be a bit more clear, I could set up this tensor to take a type. I can say the type would be torch.float. But as you can see, it's probably optional because in here I didn't actually specify it to be a float, and it works. But just like to be a bit more clear, and scatter, dimension 0, and the rest is good, right? So if all of this is working, let's go ahead and just save that again. So in the test data itself, you also have the target, so you also want to modify that. So just copy and paste them. So let me save all of this, quit this out, and then run it again. So Python, it's not called labels, it's called targets, and they have been renamed in the latest version of that. Before that, it wasn't called data, it wasn't called target, but it has been renamed to targets now. So let's just call it targets there, run it again. The training and the test data, the targets are now transformed into that one-hot encoding vector. So now it's going to be a one-hot model. So you need to modify the images as well. Or you could modify the title to look at this tensor and decide that, okay, if this is the case, then you just find the first image, and that would be t-shirt. So let's clear the screen. If I take a look at this, let's say this is label. This is a tensor. So first thing I want to do is to convert that to a list. I can do that with label. Okay, so now that's a list, and I can still see that this is the one I want to extract, right? I could just say something like take the index of that and find the index where the value is 1 point. Maybe just run this. Okay, that is good enough. So this is exactly what I want, and I could just copy this and replace the plot title with this. Okay, so a little bit, it's not as clean anymore, but it still works, right? So this is the, now it's, this is modified to account for the one-hot encoding, right? Maybe there is a faster way to do that. Anyone in the comments, if you're a Python expert, you found a better way to do it, let me know. I'm just doing it on the fly, but it works. Let me try and just save off this and try to run it again. And there you go. So you have the bag, you have t-shirt, sandal, dress, shirt, sandal. All right, that's cool. So that's kind of it. That's how we bring in data, and we bring in the transforms to tensor, lambda, and we write our own sort of one-hot encoding function. We bring that in, then we modify stuff to account for, we modify the title, the plot title to account for that one-hot encoding. We also quickly demonstrate a couple of ideas, like for example, taking data and putting down to GPU, because later on when you want to do training, you can use your accelerated GPU accelerated device to do all this training, which speeds up your training time, your neural network training time. All right. And with that, we conclude the lessons for PyTorch datasets, data loaders, transforms. I'll push all of this code on GitHub if you want to just have a place for reference. And in the next lesson, we're going to look at building models using the AutoGrad and optimization, and how does a neural network construction process looks like using PyTorch. So see you in the next video. Bye.